This is Jeff Mucci with RCR Wireless News, and we're here today with David Hammerwall, Strategic Product Manager for Ericsson's Radio Group. David, thanks for joining us today.
Thanks a lot, Jeffrey. It's good to be here.
Well, Ericsson had an announcement last week with Orange about IoT trials over LTE and GSM, and it really talked about three primary points: improving indoor coverage, reducing IoT device cost, and extending battery life. So what I'd like to do today is talk a little bit about each one of those bullet points and get your take on how that works and the impact it's going to have on Orange's bottom line.
Excellent. Yeah, we're very excited about these new developments on bringing cellular IoT to the next level.
Well, let's dive in by talking about improved indoor building coverage. And it specifically, the press release talks about improving indoor gain by 20 decibels, or dBs. How are you going to do that?
So we're very excited about this because we can do this by a pure network software upgrade. And this is a very cost-efficient way to reach additional coverage for operators. And in particular, it works by adding redundancy. So you repeat the transmissions multiple times. So you give the devices and the network multiple opportunities to decode the messages. So by adding this to all of the radio channels, you are able to then extend the coverage by up to 20 dB, or in other words, going to 7 times the area coverage, or going from basic indoor coverage to fully underground basement coverage. So it's a quite dramatic increase in coverage.
Well, your press release talks about, in Europe, there's you got a lot of concrete and brick buildings, a lot of the industrial guts of office buildings and apartments are truly in the basement. Can you talk about some of the vertical markets that you see yourself going after with this enhanced indoor coverage?
So when we look at the indoor coverage, I think one quite obvious use case is the energy meter use case. So many of these power meters are mounted in the basements where you have the power supply to the buildings coming in. And then you want to have the connectivity by this energy meter. So then you have a lot of installments in the basements, in particular in dense urban areas. This is where you have these power meters.
Mm-hmm. And going back to the 7-fold increase in range of low-rate applications, are you increasing the power output from the base stations, or just go a little more detail about how the technology is really going to work?
Yeah, so this is the beauty of it, that you don't have to increase any transmission power, not on the device side and not on the network side. So that means that it has absolutely no impact to the hardware. So this is applicable to our entire installed base based on a software upgrade, a pure network software upgrade, and additional on the device side, they also need support in the software stack for this. But instead, you rely on the physical layer or the radio protocol, where you add new redundant transmissions to increase the range. So you get multiple opportunities to decode the message instead of doing it in a limited time in current LTE that is more focused on high performance and low performance. And also, to give some compliment, this technology is applicable both to LTE and GSM. And what we're trialing now with Orange is the extended coverage GSM. Mm-hmm. So this technology to reach an extended coverage mode by software upgrade is very similar in the two technologies. It's all about adding this redundancy in the transmissions.
And so where does the software upgrade actually take place? Does it take place in a virtual EPC, or does this take place at the radio head baseband unit? So
when it comes to the extended coverage, that is primarily a baseband unit software upgrade. And also on the device chipset side, they need the software to understand these new redundant transmissions. And then there is some minor impact or less impact to the EPC in order to separate different coverage classes for the actual paging and transmissions and so on. But the main impact on the most radio channels is indeed in the baseband unit.
What impact will it have on the existing macro or small cell radio resources available for the existing coverage?
So that's a very good question. So nothing comes for free. So when you start to extend the coverage, that of course will eat more radio resources. So I think that the main purpose of the extended coverage is that you will also reach a limited fraction of the devices that are in extended coverage. The intention is not that 100% of the devices shall need 20 dB extended coverage. So for most of these use cases, the vast majority of the devices are still in normal coverage. But the last 1 to 2% of the devices might need this extended coverage to be reached. And if you need custom installations for these 1-2% of the devices, that becomes so costly that the entire business case might be at jeopardy. Mm-hmm. So by spending additional radio resources for this limited number of devices will then give you a holistic solution where you can address the larger number of devices. So in short, you trade some radio resources in order to get this full coverage.
Where would you see the DOT fitting into this particular offering? My understanding was the DOT was really designed to help extend coverage indoors as well.
Certainly. So I think that the indoor solutions are an excellent way to offload the macro networks. And they will offload the macro networks both when it comes to IoT and MTC, but they will also offload when it comes to mobile broadband. So looking at the enterprise segment, we know that the indoor coverage will be really important in order to roll out the DOT services. And of course, if you have indoor IoT devices, those will be very effectively offloaded from the macro by the DOT system as well. But considering that there is a lot of indoor deployments where we do not have custom indoor solutions, then it's very useful to have the macro reach those remote areas as well.
Got it. Well, let's move on to reducing how Ericsson is reducing IoT device costs. What can you tell us about the partnership with Sequans?
So here with Sequans, we're now testing a number of sub-features that are targeted to reduce the device cost specifically. So there has been, in particular for LTE, in GSM, we're already at quite attractive device cost levels. So it's more focusing on optimizing the cost levels for LTE devices. So there's a number of things that we can do when we go down this path of simplifying and making things cheaper to connect an LTE network. And a first feature that we're now evaluating together with Sequans is half duplex FDD. And that's a feature where you limit the device capability to transmit and receive simultaneously. So you take turn by talking and listening, and thereby you can simplify the radio parts in the device. So you, for instance, do not need a duplex filter to separate the uplink and downlink signaling. Mm-hmm. So by having this simplification on the radio module, you can significantly then reduce the cost of the device. So that is one specific sub-feature that we're evaluating. And another important element is the number of receive antennas. Mm-hmm. So current default for LTE is that you have 2 receive antennas to increase the downlink link budget or range. But it also costs a lot to integrate 2 antennas in an end device. So that's the second step that we're talking about, where we simplify now to go from 2 to a single receive antenna for LTE devices and modules. And that obviously reduces cost. And the third component is actually to reduce the peak rates. So here we go down to 1 megabit per second as a peak rate for these devices. And combined, these 3 elements will significantly reduce then the device cost.
And is reducing the peak rate, is that done at the system on a chip level, or is that done in combination with the EPC and the baseband unit?
So this is a pure layer 1 restriction. So it basically limits how much data you can transmit in any given time instance. And that will implicitly then determine how much processing the device needs to be able to compute in, say, 1 millisecond. Mm-hmm. So by reducing the number of bits that is transmitted in this 1 millisecond, you limit the processing power needed in the device.
But again, is the intelligence done at the chip level, or is it done at the by Ericsson in the radio?
So I think that the main intelligence is in the radio, or in the baseband unit, where the scheduler makes sure to not allocate more than a certain number of bits. So there you impose a restriction in the scheduler to not over allocate bit rate.
So what impact, and we're going to talk about the extended battery life in just a minute, but if you're a carrier like Orange implementing this solution, what are some of the challenges, and it's probably the wrong word, but what are some of the transition requirements to optimize your network to be able to accommodate this IoT capability? And what I mean by that, if you talk about scheduling, if you're allocating resources at the radio level or at the core level, where is that work being done? Is it at a NOC level, or who's doing that implementation?
So I think that from an operator perspective, it's not so much difference from when we look at normal LTE devices, where we have a peak rate race. So we have original category 4 devices that support up to 150 megabits, and then we have category 6 devices with carrier aggregation going to 300 megabits per second, and we have devices going to 450 megabits, reaching 600 megabits within short. So there is already a diversification in the bit rates that are supported, and this is merely a way to go down in bit rate instead to scale down the complexity. So from an operator point of view, there is not too much configuration or dimensioning to be done. It's pure managed by the network infrastructure. That said, of course, when you have a restriction on the device side to not pursue the higher bit rates, they will indeed consume more radio resources when they are in good coverage, for instance. So they can consume a little bit more than necessary to comply with the cost-saving restrictions.
Got it. In terms of managing and monitoring the service level agreement associated with this new level of service, will carriers be able to use the existing Ericsson network management system or SLA type management system, or will they have to will they be using the existing carrier network monitoring and management system?
So we don't see that there are any particular differences to manage with these devices in these aspects. So the current solution should be well adequate to maintain that.
Okay. Well, let's talk about the extended battery life. How does this solution go into the power saving mode and really help me understand how it's going to help these low power sensors remain in place for 10 years or longer without having to be replaced?
Yeah, so we're very excited about bringing cellular technology to also comply with a very extended battery life. So this is done by a number of different sub-features. So I think that the primary feature now trialed with Orange is power saving mode, which is standardized in release 12 of 3GPP. And it's actually applicable to both LTE and GSM, and also for 3G for that matter. We now trial it with LTE. And the main technology that enables a battery life is that you avoid having a lot of activity enforced by the device. So for instance, in normal LTE, you have an idle mode and an active mode. And obviously, idle mode is intended to have a power saving benefit over the active mode, where you have less frequent transmission. But also in the idle mode, the device needs to listen to paging very frequently, approximately once per second. And by adding now a new state to LTE and GSM, which is called the power saving mode state, you can reduce the number of the frequency where the device needs to listen in to the network. So essentially, instead of listening once per second, you only listen in maybe once per day or a few times per day, and going into a very deep power saving state. And then that has a few implications. One implication is that in between activity times, the device will not be reachable by the network. But on the other hand, most of these sensor type applications are very uplink focused. So take a smoke alarm detector, for example, it will maybe report once per day that it's not malfunctioning, that it's well operational. And then, of course, when there's a smoke alarm report. So then it's perfectly fine to have this that is not reachable by the network. And then the device just goes into idle mode and active mode when there is an activity. So essentially, you make a trade-off. It's not so reachable by the network, and thereby you can dramatically increase the battery life.
What type of tools is Ericsson planning on offering carriers to help define the command and control policies associated with this IoT network and these IoT type sensors?
So I think that's a quite holistic question. So we have a lot of device management and service enablement platforms to implement these kind of services. I think that when it comes to power saving mode, there is one particular element that the device is not reachable at all times. And here we're looking into options for the wall packet cord, for instance, to temporarily buffer some of the downlink signaling until the device is actually reachable. So you do not have to worry about that from the application development perspective. But overall, the power saving mode ultimately should be quite transparent to the service implementation of service enablement.
Got it. Well, the Senior VP of Orange Labs talks about, in tandem with this trial, GSM LTE trial with Ericsson, they're also deploying a LoRa trial. How do you see carriers managing long-range, low-power type networks with traditional cellular, 5G, 4G type LTE networks?
So I think that as of now, a lot of operators feels a lot of pressure to bring these services out to market. So pursuing unlicensed technologies can be one way to meet market demand in the short run. On the other hand, we believe that cellular IoT solutions will provide a larger interoperability and more scalable solution going forward. So down the road, we believe that operators will see a very attractive and cost-effective solution in the narrowband or in the cellular IoT offerings.
Well, where else is Ericsson involved in these type of trials, or where else would you expect to do trials in the GSM or 3 LTE bands?
So we have interest from most markets for these technologies. So we are in collaboration with a large number of operators on essentially all relevant markets. So I think that's a common theme now among all operators, that IoT is on top of their agenda. So we will see a lot of activities over the next months and certainly over the next year.
Good. Well, David, thank you so much for your time. Is there any other final key points that our readers should be aware of as it relates to this radio technology and chip technology?
No, I think that the overall 3GPP community has really identified some of the hurdles that have been holding the cellular IoT space back, and they are very actively being addressed now. And given the great interest in the industry and the large push from operators to accelerate this to market, we've had a very successful response now from 3GPP and also from all of the network and device manufacturers to bring this to market as soon as possible. So we're very excited over the coming year to see this technology being very mature and come to market.
Great. David, thanks for your time this morning.
Thank you very much. Good to be here.